computer. I'm going to admit some more people in the room here. There is a note in the chat to remember to take that survey for signing up for SI sessions. SI sessions really do help. I mean, it'll definitely at least half a letter grade, if not a whole letter grade, by going to at least 10 of these SI sessions. They have really cool statistics at the SI program over on the other side of campus that shows that that will be very good for you. And I highly recommend it. It gives you another opportunity actually to be kind of social in a distanced sort of way as well. You could talk with other students and our nice SI instructor, Sheila. Okay, so with that note, I'd like to begin. Our first homework will be due the first week of February. So keep on top of things by looking at Canvas to see when things are due. We're going to continue today with the lecture of module number 1, Introduction to Organic Chemistry. So I'm going to go ahead and share my screen before I forget. Share screen, that one. Okay, so we should have a shared screen now. It should be that same screen I saw before on yesterday where we were presenting inside of Top Hat. Okay, is that true for everybody? Yes? Okay. Okay. All right, I'm answering something in the chat there. I will forward that to your instructor. Okay, can everybody see this screen that has the join code and the Top Hat thing? Yes, all right, great. Let me make sure I'm not muted here. I am not, okay. Volume up. And everybody can hear me and everybody can see. So what I'm going to do, go ahead and we're going to start the presentation. And I'm going to actually figure out where we are in the slides because I know we're done with those already. We've done our orbitals, we've done our orbital filling, we calculated out our formal charge. And I believe we stopped there and we were going to actually do a couple more formal charge calculations, if that is correct.
We were on Lewis structures. Most of the time, formal charge will be 0.
Okay, Lewis structures most of the time would be 0. So that would be this one. All right, there we go, thank you. So that's slide 33. So most of the time they are 0. And so what this means is that the net charge of the compound is 0, but everybody has a full octet. Everybody has brought in and shared the number of electrons they have, okay? So the best thing about this is that if you have something with a formal charge but can move a lone pair such that neither of two different atoms have opposing charges, that will actually make it a more valid Lewis dot structure. So assuming, let's say you had something where you had an oxygen and a carbon that were right next to each other, and the oxygen had a -1 charge and the carbon had a +1 charge, by moving electrons from that oxygen to form a double bond between those carbon and oxygens, both charges will go away, okay? Now, if you still move all your electrons around and you still end up with a charge, this typically happens when you only have one charge. If you have a positive and a negative charge on the same compound, it's likely that you can move electrons around to get rid of that charge, okay?
We can't see your current slide.
I can't see the current slide. Stop share and share the slide. Screen sharing. Okay, can we see the current slide?
Yes.
Okay, interesting. Okay, so maybe I need to make sure. So please ping in and double check if you can't see the current slide. Okay, so In a Lewis dot structure, if you have a positive and a negative charge, move electrons around till those formal charges go away. But if you have just one charge, a positive charge or a negative charge, that can be a valid Lewis structure as a polyatomic ion. Now, if you have a negative charge that persists, it needs to be on the most electronegative element or the more electronegative. For example, if you have a negative charge and you have a carbon and an oxygen, oxygen is more electronegative. That's where the negative charge will reside. If you have a positive charge, you need to put it on the less electronegative atom. So if you had a positive charge and you had a carbon and an oxygen, the positive charge needs to be on the carbon, okay? So, but try to move electrons around till your formal charge is 0. If you just have one charge on there, make sure you follow those rules. Okay, there we go. And so an example of that would be to have this compound here. We actually show that it has a formal charge of +1 on the phosphorus and -1 on this oxygen. Okay, so the oxygen is the more electronegative atom. The phosphorus is the less electronegative atom. However, the fact is that we can move electrons from this oxygen to create a double bond between the phosphorus and the oxygen to make the net charge of each of those 0. Okay, so notice that we actually end up with a total of 10 electrons around here. Remember, each bond is 2 electrons. And so when we have those third row elements like phosphorus and sulfur, we can have 8, 10, or 12 electrons around those, and those will still create valid dot structures. But all of that second row, like carbon, nitrogen, oxygen, must have only 8 electrons. Okay. So this is a great example of how, by calculating your formal charge, you can see you can move your electrons around a little bit to get the most appropriate Lewis dot structure. Okay, hey, we're up to 80. Okay, so let me show you some of the things that are common Lewis dot structures for both charged and uncharged species. So we're going to be doing these things where we can have a positive charge. And notice on all of these, the positive charge is on the the less electronegative atom. For example, the carbon is probably the less electronegative atom on all of these. Here, the positive charge is actually on the nitrogen because we're using that lone pair on that lone pair that was on that nitrogen to make that bond. And so that's why the nitrogen actually has the positive charge on it. Now, if we go to other species like this, where we can have a protonated oxygen species, we can have a positive charge on that oxygen because all the other orbitals are filled, and that's the only one with a deficit of electrons. Okay, and then we can even have a positive charge on a halogen if it's bonded to 2 different things. Okay. So then within neutrals, what we'll have is valid Lewis dot structures. Most of the time, carbon's going to have 4 bonds. Most of the time, nitrogen's going to have 3 bonds and a lone pair. Oxygen's going to have 2 bonds and 2 lone pairs. Halogens will have 3 lone pairs. Okay, now notice that boron here only has 3. Boron's one of the weird ones that does not have to have 8 electrons because it only has 6 protons in it, and therefore having 3 electrons in its outer shell satisfies it. Okay. Now, if you have unpaired electrons, they can reside on almost any atom, but they tend to reside on the more electronegative atom. Now let's move over to -1 charges. What this means is, of course, our formal charge is negative, and they tend to be on the more electronegative atom, and these are on the less electronegative atom. So on this case here, the only place for it to be is on carbon. So we can actually have a positive or negative charge on carbon in many cases, okay? In addition to that, if we take boron and add that extra electron to make that 4th bond here, it gives it a -1 formal charge. And then we also will come across these anions right here where nitrogen is carrying the anion. And if we take a proton, we can easily have a negative charge on oxygen. This would be the organic equivalent to hydroxide. And then of course, halogens can have a negative charge on them. And notice all of these negative charges here, they actually have a full octet and a formal 1 negative charge. So these are all common structures we'll see as we go through both semesters of organic. Okay, so how do we convert a bond line structure to an expanded Lewis structure? What I mean is, how do we know where all the electrons are so that we can count calculate our formal charge? So chemists are lazy, okay? So when we look at these line bond drawings, it is a shorthand version of all the different bonding types we have available to us in organic chemistry. So in all of these, if you have just a line, that technically represents a carbon atom bonded to a carbon atom, okay? So if it's just lines and sticks, assume everything is carbon atoms, okay, between those bonds, okay? If the atom is anything other than carbon, it will be noted, as in the case of, oh, here's a fluorine bond, here's 2 bonds to oxygen, here's nitrogen here. Okay, so that's the first thing we need to know, that the stick is equal to a carbon bonded to a carbon. Okay, now the second thing we need to know about that is that when we have this end of our stick line drawing, we also assume that there are as many hydrogens as can be on there to get our 4 bonds to carbon. So that means that in our stick drawing here, we have our carbon bonded to this other carbon here, but we now assume that because this carbon is only bonded to one other carbon, it has 3 hydrogens on it, okay? So what we want to do is every time we look at one of these stick drawings, you need to in your mind say, oh, how many hydrogens are on that carbon? And it's just by the number of bonds you have minus 4, and that's going to give you the number of electrons, or 4 minus the number of bonds you have. So for example, this carbon here is going to have 3 hydrogens on it. This carbon here has 1, 2, 3 bonds. So there has to be 1 hydrogen there, just 1, okay? This has a fluorine bonded to it and a carbon bonded to the other side, which means there are 2 hydrogens assumed to be in this line drawing. Okay, so does that make sense? The sticks are a bond between 2 carbons, which means the ends of each of these, every time you have a bend in a system, that represents a carbon. And you assume there's the number of hydrogens required to make a total of 4 bonds to carbon. Okay, so let's apply that rule to the next carbon over, this one right here. That carbon has 1, 2, 3, 4 bonds. So how many hydrogens are on that carbon?
0.
0, because we wanted 4 bonds to carbon. 2 of those are to oxygen, 1 is to nitrogen, and 1 is to carbon. It is completely satisfied, so it's completely done. Nitrogen, we know we want 3 bonds, and so we're going to figure out where the electrons are. But now let's look at this structure here, okay? So we have, let's just look at this 1 carbon here. We have 1 stick here, 2 sticks here. So that's a total of 3 bonds. So how many hydrogens are on that carbon?
1.
1. So you can always assume that. So here we have 4 bonds to carbon. Here we only have 3 bonds to carbon. So we have to assume there's a hydrogen here. Okay, so that's the first thing we need to know about line drawings is the sticks represent a carbon-carbon bond and the hydrogens are assumed. Okay. So the next thing we want to do is we want to locate all of these carbons right here. And we need to make sure that in our minds, we convert those to having carbons at each end of the sticks that are labeled, okay? So you can't forget to add a carbon to like this point here because we need to assume those are there. The next thing we do is we now do that same thing where we add the total number of hydrogens so that we have 4 bonds to each of the carbons. Notice I didn't say the other atoms, I just said the carbons because we know carbon wants 4 bonds. The next thing we do is we now add the lone pairs. Okay, so all the carbons here have 4 bonds now. So all the carbons have no lone pairs, but we know that oxygen should have 2 lone pairs and nitrogen probably has 1 lone pair. So we need to add those in to make sure we know where they are. And then nitrogen also has a lone pair on it here. So now each atom in this structure, except for the hydrogens, has 4 electronic zones. Those 4 electronic zones lead into the shape of the molecule. Okay, so if we have a charge present, we need to make sure we can account for that charge. So for example, if we have a positive charge here on the center carbon, that means that we have a lack of electrons and we don't have an electron there and we don't have a hydrogen there. If we had a hydrogen there, we'd have 4 bonds and it would be satisfied. The fact that it has a charge means it does not have 4 bonds, but it also lacks an electron. The opposite is true when we have a negative charge on carbon. We actually have to put the electron that balance the charge out plus the electron to make the negative charge. So this is one of the times when we have a lone pair on a carbon atom, is especially when it has a negative charge on it. Okay, all right. So this leads us into what we call our valence shell electron pair repulsion theory. Okay, so we took our stick structure. We added where all of the bonds actually are, including the hydrogens, and then we added all those electrons, those lone pairs. Those lone pairs are important because lone pairs and bonding electrons take up space because they all have negative charges, the electrons have negative charges, and they force each other apart. Okay, so the idea here is that any place you have electrons in space, they're going to try to repel each other as far as possible without breaking our bonds. Okay, so we need to take into account the bonds, the bonding electrons, and the lone pairs. And that controls our 3-dimensional shape of our molecules. So there's a bunch of different electronic domain geometries. So here, all we're talking about is where are the electrons, okay? So in the case of this, if you only have a single bond between here and you have no lone pairs, you could have a linear geometry, meaning that you have 2 electrons here and 2 electrons here and no lone pairs, okay? So you only have 2 electronic domains. Then the other way, the next one, you add another electron bond here. So you have electrons here, and electrons here, but no lone pairs. That would create a 4th zone. So you only have 3 domains. That means that these have to be trigonal planar because that's as far as you can spread something out in 3 dimensions, believe it or not, is that flat 120 degrees apart. By adding a 4th electronic dimension, we now get to go into our 3-dimensional device. And this is what we call tetrahedral, okay? So imagine having 3 of the electronic domains facing down and 1 coming up, okay? Now, if we add another one, we have to spread all of those out in as in the 3-dimensional geometry as possible. So what we end up with is the middle of it being this trigonal planar at 120 degrees apart, but then we create an axis in the middle of that propeller to create 2 more domains that are 90 degrees from that trigonal planar plane. And then if we go crazy and go up to something, you know, some of the metals, we'll end up with what we have 6 electronic domains. And we end up with this right here. Well, this is going to be a square planar part, but then it has an axis above and below that plane, giving us what we call octahedral. All right. So this means if we just look at the electrons in a system, it controls the geometry of the molecule. Okay, so what does this really mean? Well, okay, let's think about this. If we have just a p orbital like this right here, or this kind of orbital where we have electron density on either side of the main atom, we're going to end up with this linear geometry. Now, this is now our molecular geometry. So these are our electron domains. So we can count bonds and lone pairs in electronic domains. When we talk molecular geometry, all we're looking at is atoms, the geometry of the atom. So in the case of this particular, the first one right here, we only have 2 electronic domains. They are going 180 degrees apart, and that means that our geometry is going to be linear because there are no lone pairs, okay? So our molecular geometry and our electronic geometry are the same. Okay. Now, it gets more complex once we add another zone here. So if we add another zone, we get that electronic structure that's that trigonal planar that are 120 degrees apart, like this. And if we have 3 things bonded to that central atom that have those 3 electronic configurations and no lone pairs, our molecular geometry is exactly the same. It's still trigonal planar. However, if one of those electronic domains is not a bond, then it has a single lone pair, and the molecule is now molecularly geometried as bent. Okay. Now these, let's see, can you see the bottom names on here? On this slide here, they're kind of blocked out from me. But once we get to 4 electronic domains, what we see is that we can now have a wide variety of molecular geometries depending on how many, no, okay. Let's go to zoom out. 1, 2, 3, 4, 5. All right, let me see if I can't move this up. No, 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 no. Where are you going? Wow. I was having a little trouble with presenting this yesterday as well from campus. In the past, I usually present this using an iPad, and I think I might go back to that because this seems to be giving me a little trouble. Okay. Let's present. Start presentation and stop share and reshare. Yeah, I think I'm gonna go back to presenting on my iPad because I can do a lot more with it. Okay, can we see the screen again? Okay. All right, so it's a little smaller than it was before, but now that we have 4 electronic domains, we have options for having the electronic domains be bonds to other atoms or lone pairs. So in the case, if we have 4 bonds, those are going to be spread out as far as possible, giving us about 109.5 degrees. And we call that the tetrahedral molecular geometry. So it's the same as the electronic geometry, but now it's the molecular geometry. If we only have 3 things bonded to it and 1 okay, let's try that. There we go. Perfect. Thank you. So you think, okay. All right. And then, okay. Click here. Click on the slide on top hat. There we go. Okay. So, of course, if I move my mouse, it goes away. Okay. So if we only have 3 things bonded to our system, we end up with a single lone pair. That lone pair is still a tetrahedral electronic geometry, but you end up with 3 atoms underneath it, and we call that trigonal pyramidal because it's like a little pyramid, but it's still only 3 of them. Now, if we replace one of those bonds, and so we have 2 lone pairs, our molecular geometry becomes bent. Okay, so if we go up in those, add another electron domain, this is specifically when we see sulfur and phosphorus, we're going to get to see these things. The electronic domain is trigonal pyramidal, but when we have 5 things here, again, the geometry is trigonal pyramidal, but just by taking out one of these bonds, turns out that the one of the trigonal planar orbitals is the one that's going to have the lone pair, and we get this sawhorse shape. If we lose one more bond and have another lone pair, we again lose something in that trigonal planar, and it becomes T-shaped. And then when we go to the last one, we're going to see where it is on the it turns into linear. So notice that's kind of weird because it's losing all the trigonal planars first. And if we think about it, that makes sense because these two are linear. They're 180 degrees apart. And so by losing these that are 90 degrees apart from that one, those are the ones we're going to lose to create that linear structure. And then the octahedral kind of does the same, where we go for square pyramidal, square planar right here, a T shape, and a linear shape. Again, we don't use these very much in organic chemistry, but it just goes to show you that these electronic domains control the shape of the molecular geometry because the lone pairs do take up space. Okay, so that means that if we have 4 bonds around an atom and all the atoms that are bonded to it are the same size, then we should end up predicting the correct structure. So the electronic structure for our tetrahedral structure says they should be 109 degrees apart. That's as far as we can spread them out. And now if we make a molecular structure that does that, and all of the species are the same, we end up getting that true 109.5 degrees. Okay. However, if your atoms are of different sizes, they don't. Okay, so let's go back and look at this and say, okay, so if this is our 109 degrees, they're all spread apart equally, which orbital is the S and which orbital is the P? Because the P's are on the X, Y, and Z axis, and the S is spherical. So that doesn't make sense that we would have this tetrahedral structure and have 2 different kinds of orbitals creating these bonds. So that led to some consternation within the organic chemistry crowd, because in theory, it should look something like this, where one of the things is bonded to the S orbital, and then we have one thing bonding to each end of one of these P orbitals. So that would give us some crazy structure like this, where these would all be 90 degrees apart from each other, right here, and then this would be sticking out somewhere else, okay? But we don't see this, okay? So that means there must be something else going on, because we don't see this unusual structure. We see 4 equally spaced bonds. So now we have to account for this, and we account for this by trying to blend these together in what we call a hybrid orbital. So the idea here is, when we started off with that structure, this is the structure for carbon right here. We filled our 1s orbital with our 2 electrons. We filled our 2s orbital with 2 electrons, and we filled each one of these p's with 1 electron, because there are 4 valence electrons in carbon. Why is there 5 here? No, there should be only, there shouldn't be 1 here. There should be 4 valence electrons in carbon. Okay, so what happens is that this is kind of difficult for the fact that we want to try to bond 2 things to an S, and then we have this empty P. So what happens is we blend those S's and P's together to create a hybrid orbital. So the energy for the S comes up a bit, the energy from the P goes down a bit, and we end up with a total of 4 orbitals. We have 1 S and 3 P. So we end up with 4 orbitals total, okay? We had 2 electrons in the S and 2 electrons in the P. Now by blending them all together, so we have an sp3 hybridized orbital. So we have 1 S and 3 P's blended together to make a hybrid orbital. So we have a total of S plus 3P, a total of 4, and they're all of equal energy. Okay, so how did it get to be equal energy? Well, we added a little energy to the S and we took a little energy away from the P's to blend these together. Now we have 4 equal orbitals. So when each of these orbitals bonds with another atom, that means they're going to be evenly spaced around the system. Okay, so that's the basis for the idea that we have these hybrid orbitals blending together to make equal orbitals, such that because we have that equidistance geometry around our materials. Okay, so what does this look like, right? Because the S orbital is round and these P orbitals look like dumbbells. Well, we're going to blend them together a little bit. So we're going to add a little bit of S character to one lobe of the P. So we're going to take one lobe of the P and make it a little bit rounder because it's taking up some S character. Okay, so they become lopsided. And then there's a little teeny bit down below. And then we're going to do that the same for each of these others. Notice these don't all go up and down the XYZ axis anymore because they have to spread out as much as possible. Okay, and so when we see that, we can get to where one's going to be on one of these axes, and then all of the rest of them are going to be tilted away from the XYZ axis, but they are 4 equal orbitals. Okay, so do we see how that now, because we're blending those 2 types of orbitals together, we've actually changed the shape and direction of each of those orbitals. So that gives us the hybridization we need to make these symmetrical tetrahedral bonds. So what if you have, what if you don't want to use all 3 P's to do that hybridization? Can you just do some of the P's? Well, that is actually something you can do. So what we can do is, like in the ground state here of carbon, and this is drawn correctly, we have 4 electrons. We have 2 in the S and 2 in the P. So instead of using all 3 of these P's, we can actually just use the first 2 and create 3 equal orbitals of the same energy. And we leave one of the P's orbitals completely untouched. Notice it's at the same energy. So that P orbital has not been modified, only these 3. Now, what does that mean about the shape of this sp3? Okay, I mean this sp2. It's 3 equal orbitals, meaning we have 3 electronic domains. That means this has to be trigonal planar, where all 3 of these are going to be 120 degrees apart. Okay, right here. And then this P is going to stay in its true dumbbell shape. It has not been modified. It has not changed. Okay, so why might something do this? Well, it turns out what we'll see is that it's going to help us when we do double bonds and triple bonds. We require a different type of hybridization to do this, where we have some of the S and P is blended together, and the P's, and we have 1 or more P's that stay unhybridized. Okay, so what would that look like in an orbital sense? Well, because we have the 3 orbitals that are the same, the sp2s, so we have 3 sp2s, so we know we have 3 because we have 1 from the S and 2 of these different P's to give us a total of 3, and we know that these have to be trigonal planar, okay? Now, if we have that trigonal planar structure from those sp2s, and now we add the p orbital that's untouched, we now have 5 electronic domains. So these 5 electronic domains are going to give rise to how we can bond. Okay, so these SPs, 2 hybridized orbitals, or SP3 hybridized orbitals, are the ones that make the single bonds, the bonds right in between 2 nuclei. We call those sigma bonds. Okay, now what do we do with those P's? Well, we have 1 electron in this P, 1 electron in this P, and we can have these bond above and below where the sigma bond is. Okay, so we have this above and below bond, and we call this a pi bond. Okay, so we have a sigma bonds are the single bonds in between individual nuclei. Pi bonds are bonds that are above and below the plane of the sigma bond. Okay, so if we created a plane with these atoms here, that means these pi clouds are above and below the plane created by that. So what does that mean? Okay, so if we have our sp3 hybridized orbitals creating a trigonal planar structure, that means that the degrees between all of these are 120 degrees, which makes ethylene, this 2 carbons and 4 hydrogens, completely flat molecule. But above and below that completely flat molecule is where that second bond is, that pi bond. Okay, so can we do that with just 1 and make a different kind of structure? And the answer is yes. We can take the s orbital and just use 1 of the p orbitals to create a new hybrid orbital called an sp. Okay, and because we're using 1 of the s's and 1 of the p's, we get a total of 2 hybrid orbitals, an sp orbital, and we can have 2 untouched p orbitals. So that means our sp orbital is going to be kind of linear because we're going to have a dumbbell shape here, and we'll have 2 untouched pi orbitals. Okay, which means one of these pi orbitals, p orbitals, has to be in an x direction, one of them's in a y direction, leaving us the sp in the other direction. So what does that look like? So the blue orbitals here are the ones that are sp hybridized, are the blue orbitals here. And so they create a linear space right here, and they do the sigma bonding between the hydrogen on the end here and the other carbon. So those sp hybridized orbitals are the ones doing the sigma bonding. The sp2 hybridized orbitals are the ones doing the sigma bonding. The sp3 hybridized orbitals are the ones doing the sigma bonding. The leftover unhybridized p's are the ones that are going to do the pi bonding. Okay, so in this case here, I'm going to switch colors. We have this p orbital. This is 1 p orbital here on, let's call that the y-axis, and then the second p orbital is on the z-axis. Because we haven't hybridized them, they haven't done anything. So now that gives us an opportunity to bond to the p orbital on the next atom that's in the same orientation. So that means we're going to have a bond above and below the sigma axis here for 1 of the p orbitals, and we're going to have a pi bond in the same axis as the sigma bond, but it's going to be 90 degrees away from the other pi bond. So what does this mean? That means we have 1 sigma bond, 1 pi bond above and below the plane, and 1 pi bond in the plane, giving us a triple bond. Okay, so we just went from having sp3 hybridized, giving us only single bonds, to sp2 hybridized, giving us 1 sigma bond and 1 pi bond, giving us a double bond, to only using 1 of those p's and getting an sp hybridized orbital, giving us our sigma bonds, in the remaining 2 p orbitals, giving us pi bonds. Okay, so what does that look like? Let's summarize that. So when we start with our ground state here, we have 4 valence electrons, okay? These are our core electrons. We don't care about those. So we have 1, 2, 3, 4 valence electrons. To spread them out evenly over the entire system, the first thing we can do is make them all the same and form 4 equal orbitals. When we formed 4 equal orbitals, that gives us an opportunity to do 4 sigma bonds. However, you don't have to. You can just use 3 of them. And when we use 3 of them, that gives us 3 equal orbitals, which means we have a trigonal planar geometry because it's 3 things in space. And we have 1 leftover p orbital. And that leftover p orbital can bond above and below, giving us that pi bond. And then if we only hybridize one of those, then we have 2 electronic domains, making it linear when we form sigma bonds. But then we have our pi bonds above and below the plane, but we have a total of 2. 1 for the first p orbital, 1 for the second p orbital. Okay, so what does this mean? That means that when we have an sp3 hybridized orbital, that orbital is 3/4 p and only 1/4 s, because that 1 s orbital has to be spread out over those 3 p orbitals. But if we only use 2 of those p orbitals, then it's 2/3 p, 1/3 s. Okay, and then the last one is half p, half s. What does that mean? That means that the orbital deformation is different. There's less of this is the smallest differentiation, where this side is only a little bit bigger than this one. When we get to this, we have more s characters, so it gets a little bit bigger, and the backside gets a little bit smaller. And by the time we get to this, we have a huge side of one orbital and a smaller one of another. So that character changes the shape of our orbital, which also changes the length of our bond. Okay, but that doesn't work just for carbon. It works for all of our group 2 elements, okay? Which means oxygen is sp3 hybridized most of the time. Nitrogen is sp3 hybridized. If oxygen or nitrogen only has single bonds and lone pairs, it's sp3 hybridized. If you have a double bond between nitrogen and oxygen to another element, that means you have an sp2 hybridized orbital and a p orbital. And if you have a triple bond between nitrogen and oxygen, it's rare in oxygen, but it happens, you actually end up with that same thing where you have an sp, 2 sp orbitals making our sigma bond and our lone pair, and the p orbitals are using to make that second and third bond. Notice that the lone pair is always in the hybridized orbital, right here. The lone pair is always in the hybridized orbital because we want the p orbitals to do that overlap pi bond. Okay, so let's review that and see how it goes for structure. That means that because sp only has 2 electronic orbital locations, that means our molecular shapes are linear. Okay, when we have sp2s, that means we start out with something that's trigonal planar, but if it has lone pairs, it changes it. So if we have this, these are trying to be 3 orbitals evenly spaced apart, that's 120 degrees. So if you have 3 things bonded to it, we ended up with that trigonal planar molecular geometry. However, if we have a single lone pair, this is our lone pair here, we have a molecular geometry of bent. Now, once we get to the sp3, I said you can have things with lone pairs in our sp3. If we have 4 bonds to it with no lone pairs, we get back to the tetrahedral. If we have 3 bonds and 1 lone pair, that gets us back to the trigonal pyramidal. And if we have 2 bonds with 2 lone pairs, that gets us back to our bent. So in this case, like for example here, in water, the oxygen is sp3 hybridized. 1 lone pair is in an sp3 orbital. One lone pair is an sp3 orbital, and the 2 sigma bonds are also sp3 hybridized orbitals. Does that make sense? That you can now see the different hybridization and how it changes the molecular geometry.
I have a quick question.
Yes.
How can you, like, just looking at it, tell the difference between the tetrahedral bit and the trigonal planar bit because the lone pairs aren't there for you to see?
Great question. Because if you're not sure, draw your Lewis dot structure. Because
Okay.
the Lewis dot structure will show you that you have a lone pair there. And that way you can like double check your work, and by drawing your Lewis dot structure, you will see the lone pairs, whether they are there or are not. Okay?
Okay. Thank you.
Okay, so let's take a break. Just shake it off, stand up, wiggle a little bit. All right, so now we're going to change gears a little bit. We talked about electrons and where they are. We talked about how those electrons have different energy levels. And we talked about how we can start blending those different orbitals to give us different molecular geometries. And the whole point of blending these orbitals is to make things symmetrical and even as possible. Okay, so now that we have that, and we know that the driving forces for these orbitals being shaped in a certain way is the fact that we have electron-electron repulsion between the systems. Now let's go, instead of within a molecule, let's go between molecules. And so I'm going to talk about the forces between molecules and how they interact together. Up to now, all we've been talking about is the electrons within a single molecule or atom. So now we're going to kind of look at it from the outside in. And we'll learn that the macroscopic physical properties change based on the type of interactions we have and the strength of those interactions. Okay, the intermolecular forces result from attractive and repulsive forces, but there's a bunch of different ways we can do that. For example, if you have a polar bond, you have an electron-rich zone and an electron-poor zone. That means we have an opportunity for electrostatic attraction. And then we also have a place where we can have charged surfaces or partially charged surfaces change our molecular forces. Okay, so the idea is that when you have something that is nonpolar, when you have nonpolar covalent bonds, the bonds all cancel each other out. Okay, so let's see what I mean by that. So if we have, this is a carbon right here, and these are hydrogens here. Carbon is just a little bit more electronegative than carbon. Okay, sorry. Carbon is just a little more electronegative than hydrogen. So what's happening is the carbon's going to pull a little bit of electron density this way. Okay, so there's that one bond has a dipole. A dipole meaning that there's a partially positive side of that vector and a partially negative side of that vector. Okay, now in the case of 4 equal atoms, these are all hydrogens, they're going to all be pulling in this directions all toward the center here, and as a result all of those forces cancel out. Okay, because they're all opposing forces. If we drew them as vectors, they would all kind of go to the middle and they'd all cancel each other out, and that means we have a non-polar molecule even though we had polar bonds between the atoms. Okay, so that is a key thing here. Okay, your dipole moment is associated with the net charge, the net polarization of the bonds here. So in the case of methane here, all of them cancel out and we end up with what we call non-polar. Okay, now let's take that same atom and move it over here and only have 2 hydrogens on here, but we're going to add 2 chlorines. These are chlorines. Chlorine is much more electronegative than carbon. So we have the carbon's going to pull electron density away from the hydrogens, and it's going to go in that direction, making a net dipole for just these 2 bonds this direction. But then the chlorines are going to pull a lot of electron density. Let me change the color here. The chlorines are going to pull a lot of electron density away from the carbon because they are more electronegative, making this part a net dipole is also in this direction. So if you add this dipole to this dipole, we end up with a net dipole for the molecule to be additive. They're both pointing in the same direction. Okay. So just by switching these atoms, we've gone from something that has a net dipole of 0 to something with a strong net dipole in one direction. So that means that this molecule is what we call a polar molecule. Okay, we had polar and nonpolar bonds. By adding all of those bonds together, we have polar and nonpolar molecules. Okay, why is this important? Polar and nonpolar molecules have different intermolecular forces. Okay, so let's talk about just some structures that we might see polarity in. And methanol, because we have oxygen and carbon here, there's a net dipole difference between them. And so we see a dipole of about, 2. So that has an available, the fact that we have that carbon and that oxygen creates a dipole in one direction. It's showing that we have that. Now, we can do the same thing with a double bond on oxygen. It's still that same effect. The oxygen is pulling electron density away from the carbon. We see a minimal effect. Now, if we just have chlorine doing the pulling, we have a net dipole going from the carbon to the chlorine. We see that. In water, we have a net dipole because we have the oxygen, and we're only looking at the bonds where the hydrogens are in this direction. The lone pairs here don't contribute to the dipole moment, but we have a net dipole in that direction. So ethanol is similar to this one right here. It's called ethanol. It's similar to the methanol structure. Ammonia also has a dipole because it is trigonal right here. And so it has a net dipole in that direction. This is getting less and less of a dipole. Notice that when we get to carbon and hydrogen bonds only, our dipole drops to 0 because carbon and hydrogen are basically that almost a nonpolar bond. And so they basically cancel each other out as we go through the molecule. So hydrocarbons like this, or things with only carbon and hydrogen, tend to have no dipole and be non-polar. Now, what if you had something 4 really polar bonds, but they're all pulling in the opposite directions? We end up with a net dipole of 0. Notice previously, if we only had 2 chlorines on there, we had a strong net dipole. But by having all of those polar bonds cancel each other out, we go back to having a non-polar compound. Okay, let's see, we're there, nope. Okay, so what does that mean? So because we have this pulling of electron density from one side and the other, we can actually say that that bond is polar, okay? Now, if we add all of the bonds together, let's see, I have a question. Will the net dipole always be in the direction of the most electronegative atom? Yes, that is true. The net dipole will always be in the direction of the most electronegative atom, because notice our dipoles, the positive side is this tail end, the pointy side is the negative end. So this is the positive side and the pointy end is the negative side. So the net dipole will always point in the direction of the more electronegative atom. So again, this is a polar bond. We already talked about polar bonds, but now that we have 2 polar bonds, we now need to know that net dipole. Now notice that, and before when we talked about those polar bonds, we had the negative side, which is typically denoted as red, and the positive side typically denoted as blue. Here, now the whole shape of the molecule still has half of the molecule seems to be partially positive, and half of the molecule seems to be partially negative. Okay, so this tells us we have a polar molecule because of that. And the difference between this here is because we only have 2 things bonded here, each of these hydrogens is about 0.44 of a positive charge, which means this is not quite a negative charge, but it's getting close. However, if we take away the ability for it to donate materials by having something that the carbon itself is pulling electron density away from these nitrogens, and so that carbon can't contribute as much to this oxygen. So notice how this oxygen is not as electronegative as this oxygen in the system, because this CH3 group cannot contribute as much. Okay, so molecular structure will change the dipole moment even if you have similar atoms. Okay, so that tells us that molecules have inherent dipoles, okay? But now let's talk about the specific molecular interactions. We have 5 primary types of intramolecular interactions, the reactions between different molecules in organic chemistry. And I'm going to go from strongest to weakest. The strongest one we have is what we call ion-ion. So if you have, a positively charged carbon next to a negatively charged nitrogen, those are going to be the strongest bonds. And think about, just look at, sodium chloride melts at 2000 degrees, and something like a methane, boils at minus 200 degrees. So they have different intermolecular forces, but the ion-ion forces are by far the strongest. So now, if you have something like an ion, like a sodium ion, dissolved in a polar solvent, that's the next strongest intermolecular reaction, and that's what we call an ion dipole. So it's not a positive charge and a negative charge, it's a positive charge and the negative side of an atom, the more negatively charged side of an atom. So that's the ion dipole, and that's about an order of magnitude weaker than the ion-ion. The next thing we have is when a hydrogen from a neighboring molecule can bond to the lone pairs of a neighboring molecule, of a different molecule. And that's the next strongest intermolecular force we have. In fact, it's the most common intermolecular force when you don't have ions. It's the strongest one we have. And it is two orders of magnitude weaker than that ion dipole. Okay, so I'll explain more about hydrogen bonding in a little bit. Dipole is when you have a polar molecule here, it's got a positive and a negative side. You have a polar molecule here, it has a positive and a negative side. So the positive side is going to orient to the negative side of the molecule next to it. And that's what we call dipole-dipole. And then the weakest of all our forces is what we call a dispersion force, meaning we have a non-polar molecule with no polarity to it at all. But when the two molecules get close to each other, they try to induce a dipole. One will try to become partially negative and one will try to become partially positive. Okay, it can't really do that. It doesn't really have strong bonds. So that's why it's our weakest force. And we call that a London dispersion force or induced dipole. And I'll describe each of these with diagrams in a minute. Okay, so the ion forces are strongest because you have a full negative charge being attracted to a full positive charge. So that's why it's our strongest force. In relation to that, we have the ion dipole, a full positive charge being pulled toward a partial negative charge, which means one molecule cannot completely satisfy the charge on this atom, and we end up having to put many of these waters around this sodium ion to counterbalance that charge. That's why it's so much weaker, because it can't give a full charge balance between the positive and the negative. Okay, and then hydrogen bonding. Hydrogen bonding, well, is going to be used a lot. So knowing why this works is kind of important. So the idea here is that in most of these, like hydrogen carbon bonds and hydrogen oxygen bonds, there's a slightly positive side, which is the hydrogen, and a slightly negative side, which is, let's say, oxygen, right here. And then the oxygen actually has lone pairs on it, okay? So the partially positive side of the hydrogen here is attracted to the lone pair of the other molecule. When a hydrogen is attracted to the lone pair of another molecule, it has hydrogen bonding. Notice it has to be partially positive. In the case of the carbon-hydrogen bond, this is almost nonpolar. So these rarely contribute to hydrogen bonding. When we see hydrogen bonding as things like alcohols where we have an OH, excuse me, or we'll see them in carboxylic acids where we also have an OH group. We also see hydrogen bonding in polar bonds like nitrogen-hydrogen bonds, etc. But this is a nonpolar bond. So we think about hydrogen bonding between a hydrogen attached to some kind of oxygen or nitrogen or sulfur. Okay, so it turns out to be one of the stronger forces we have in organic chemistry because it changes the boiling point of our system quite significantly. Okay, so let's compare a couple things. So let's say we have something like this where we have a strongly polar bond. We have a hydrogen to an oxygen, and it has lone pairs. And we have a hydrogen to an oxygen on this side, which means, excuse me, this hydrogen can be attracted to the oxygen on another molecule. This hydrogen can be attracted to an oxygen on another molecule, meaning it has two different places for it to hydrogen bond. Now, a hydrogen from another molecule can now bond to these two lone pairs here. So we end up with a total of 6 possible places for hydrogen bonds, 2 for the hydrogens on the molecule and 4 for the lone pairs on the molecule. Okay. So if we take away one of these hydrogen bonding possibilities by taking away this hydrogen and replacing it with a carbon, notice we now have a carbon bonded to oxygen and a carbon bonded oxygen. We've taken away the hydrogen bonding from this side of the molecule. However, this side of the molecule, this hydrogen can bond to another molecule. We still have 1, 2, 3, 4 lone pairs. So we still have the potential for molecules to bond to the oxygens with their hydrogens, but we only have 1 hydrogen available for hydrogen bond. And so it doesn't have as high a boiling point. We've gone down in the number of hydrogen bonds available. And if we take away this hydrogen so that these molecules can't hydrogen bond at all, remember, this is not a polar enough bond to hydrogen bond. We no longer have any hydrogen bonds because there's no hydrogens to bond to these, and the boiling point drops again significantly. So the boiling point related to this is more about the molecular weight of the system than the ability to hydrogen bond. All right, no question. All right, we're doing good on time. Okay, so now let's go to the next one. So hydrogen bonding, you must have a hydrogen on an oxygen or a nitrogen. The sulfur hydrogen bond is actually so weak it barely hydrogen bonds. So look for that. Okay, the next one is dipole-dipole forces. Now in that, we look at the total charge or the total dipole moment of an atom, and we look at the, molecule. We look at the negative side, and then we look at the positive side. And what can happen is, in the case of this molecule here, we have a strong negative side and a pretty strong positive side. And so when these order in solution, the positive side of one molecule is going to associate with the negative side of the other molecule. Now this one also hydrogen bonds. So let's go to one that can't hydrogen bond. So in the case here, oxygen is still the more electronegative atom. And so that the chlorines are the slightly positive side of the atom. That means that when another molecule of this, the chlorine is going to associate with the oxygen of another molecule as it comes up. Because the oxygen is the negative side of the molecule and the chlorine is the positive side of the molecule. Okay, so that brings us to our last one, the weakest one. And this happens mostly in non-polar materials, things that only have carbons and hydrogens on. And the reason this works is that the carbon-hydrogen bond is not, it's slightly polar. It's 0.4 difference in electronegativity. Remember, a polar bond starts at 0.5. But what can happen is as one molecule comes near another one, it can transfer some of the positive charge to the other side of the molecule and some of the negative charge to the other side of the molecule, allowing it to be attracted by its neighbor. So this is a little tiny, tiny bit of a positive charge transferred, a little bit of a tiny, tiny negative charge transferred, and that allows them to line up and have this induced dipole. However, because those are nonpolar bonds, surface area is very important here. The more available space you have to bond between these two, the greater the effect. So that means long straight chains are more likely to do this induced dipole bonding than spherically shaped molecules. If we have a spherical shaped molecule, we have very little surface area in comparison to these longer molecules. So the shape of the molecule can control the boiling point as well. So the boiling point of this is very low. It's barely above room temperature. Room temperature is 273 Kelvin. So it's barely above room temperature. And the only reason it is because of this induced dipole-dipole force and its molecular weight. However, neopentane is the same molecular weight, but has a lower boiling point because it has less surface area in that induced dipole bonding. Okay, all right. Okay. All right, so we have five types of intermolecular forces. Now let's talk about how it changes their physical properties, things like melting point, boiling point, etc. And also how we can dissolve things in others like miscibility and solubility. So melting point, by definition, melting point is when we give the molecule enough energy such that the solid it has they can move past each other and become a liquid. Okay, so melting point is actually a phase transition. It takes heat to heat up the material. It takes heat to go through that phase transition. Once it has enough heat to go through that phase transition, it is then a different phase. Okay, now the stronger the intramolecular force, the higher the melting point. So if we look at this ion-ion interaction here for lithium fluoride, it melts at 845 degrees C, okay? However, if we go to smaller molecules of about the same molecular weight, notice that these all have about the same molecular weight. So we're comparing, molecular weight. We're only looking at the forces, how they affect. With hydrogen bonding, we have a boiling point of negative 97 degrees C. However, with the dipole-dipole interaction, we can have a negative 92 degrees melting point, which is a little higher. And the London dispersion forces is the weakest force we have, and therefore it has the lowest melting point. Okay, the stronger the intermolecular interaction, the higher the melting point. Okay, so by definition, boiling point is where we go from another phase transition. We go from the liquid, it has to have enough energy for all the intermolecular forces to leave, and so that it can come out into the gas phase completely. So when we're boiling here, we have those dynamic forces as they move past each other, but you have to break all of those to get up here. Okay, so the same trend applies. The stronger the dominant intermolecular force is, the higher the boiling point. So in the case of this ion-ion interaction, the boiling point's really, really high. Hydrogen bonding actually has one of the greatest effects on boiling point of any of the intermolecular forces we have in organic chemistry, and it has the highest boiling point here. The dipole-dipole is the second strongest and therefore gives us the next increase in boiling point. And then our London dispersions are the weakest of the set and therefore have the lowest boiling points. All right, does that make sense? The stronger the force between this molecule and that molecule, the higher the melting point will be, or the higher the boiling point will be. Okay. So let's look at things with weaker and weaker dipole moments, okay? So the dominant molecular force has to be, is going to be the one that we look at first. However, if you have it having now competing forces, you can see an interesting change. So in the case of this right here, we have a material that probably has a dipole-dipole force as its major force. It has a boiling point of about -24. By adding a little bit of molecular weight, we're adding some of the boiling point due to that molecular weight, but we still have that dipole-dipole force as our molecular, as our dominant force. Now, by adding a little more molecular weight, adding another carbon here, it goes up again. But again, dipole-dipole is our predominant interface here. And when we get to this one here, we've actually started to have dipole-dipole is still our stronger one, but we're starting to get this longer chain. This longer chain can now start contributing too, because it has a weak London force in it, but the longer and straighter these chains are, the more and more London forces can apply. And we have an increase in boiling point again. So molecular weight increases boiling point and melting point. The strength of the interface of the intermolecular force increases them. And the surface area in London forces increases them. Okay, so how does that those intermolecular forces affect things like solubility and miscibility? First of all, miscibility is the mixing of two liquids equally, so there's no phase in between them. Solubility tends to mean dissolving a solid into a solvent, okay? So in general, if molecules have the same dominant intermolecular force like hydrogen bonding or dipole, they tend to be miscible or soluble in that compound. So if you have 3 kinds of alcohol, they're probably going to dissolve together. If you have 4 kinds of hydrocarbons, they're probably going to dissolve together. Okay, so let's look at alcohols first. In an alcohol, especially small alcohols, the dominant force we start with in this small molecule here is hydrogen bonding, okay? Because this is the hydrogen bonding side of the molecule, and this is a very small side of the molecule, so there's no van der Waals forces, okay? So we can say that this thing is predominantly a hydrogen bonding molecule. Now let's look at water right here. Water is also a predominantly hydrogen bonding molecule, and this is hexane, which has no dipole-dipole forces, it has only van der Waals forces. Okay, so this hydrogen bonds, this does not. This only has London forces as its major force. So when we're a small alcohol like this, the hydrogen bonding dominates and we are completely soluble in water, okay? And only a tiny bit soluble in that nonpolar solvent hexane, okay? Now, why? Well, because the hydrogen bonding is the dominant force and therefore it's going to barely dissolve. Once we add another carbon, now we're starting to get a little bit of van der Waals forces coming off here, but we still have our OH as our dominant force. That means it's completely soluble in water again, but it's also soluble in the nonpolar solvent. If we add another carbon here, we're starting to make this our less dominant factor because we're having more of this nonpolar side. We still are completely soluble in water and completely soluble in hexane. But as we get bigger and bigger and bigger, the longer that chain gets, the less the hydrogen bonding works and the more the van der Waals forces work. Okay, so like dissolves like, just because you can hydrogen bond, you have to look at the molecule as a whole. Okay, to summarize that, let's look at some things that can and cannot dissolve in something. So the solvent is the thing that is the liquid, the solute is the thing that's the solid, and what can they, what can one be dissolved into the other? So ions don't dissolve, can't be used as a solvent, so we're not going to care about it. So if we have an ion with something that is hydrogen bondable, they tend to be very soluble. So think of inorganic salts and water, okay? Because they can hydrogen bond, they can actually support that ion really well. If we move to dipoles, now we only have a partial positive charge there or a partial negative charge. And so it does have some solubility to no solubility at all. But by the time you get to those induced dipoles, those London forces, there's no force that bring those ions in, and it's completely insoluble. Likewise, things that are hydrogen bonding, dissolving each other. Dipoles can and cannot. Depends on what the dipole is. It can be fairly soluble or not soluble, depending on, for example, if you do have a dipole, but you have a long chain, you won't hydrogen bond to that, and it won't be soluble. Induced dipoles can be soluble in some hydrogen bondings, but not always. Hydrogen bonding with a dipole, usually it depends on how strong the dipole is and how strong the hydrogen bonder are. But dipole materials tend to dissolve in other dipole materials really well, or induced dipoles. And induced dipoles tend to also be soluble in dipoles and non. But things with hydrogen bonding can have fairly low solubility if the induced dipole is the less dominant effect. Okay, there we go. Okay, so that leads us to hydrophilicity and hydrophobicity. Okay, so by definition, hydrophilicity means water loving. So you think of things that completely dissolve in water. But then you can also think of things that are hydrophobic, which are things that fear water. And so hydrophilic would be something that is, like alcohols or something that dissolves in water really well. Hydrophobic are greases and waxes and stuff like that. But you can trick that because of competing molecular forces. In the case of soap, we have competing molecular forces. We have a induced dipole section here, this long chain hydrocarbon here, and those kind of want to dissolve into each other. However, you have some polar group as well. The polar group wants to be in a polar solvent, i.e. water. The nonpolar side wants to be in a nonpolar thing, or basically anything that has grease in the area. So we have competing forces. We have wanting to be out of water, wanting to be into water. So how do they accommodate this? Well, they maximize the energy by creating what we call a micelle. And so the fat dissolving, or the van der Waals forced ones, gather all together into a small group. And then all of the polar molecules completely surround it. So in this case, we're actually dissolving a non-polar compound into water by creating these micelles. And so we have the London force, the induced dipole forces are all gathered together and are being completely surrounded by those that hydrogen bond. And so that has how we have competing forces actually go to work for us in this case, this is how soap works. All right, questions. There was a question actually about a group me. It looks like somebody's starting to join. If you could please add that group me to the Canvas page. I think there's a tab for that. I don't want to be in the group me. I want you to have free reign over that. I don't want to monitor or even know. So please go ahead and look for the group me system. Also, don't forget to do your survey. It opened at 7 o'clock last night and it's open through Friday. So you need to get that in as soon as you can. All right, we're right here, right about 9:20. So I think this is my last slide actually. Yes, it is. And so I'm gonna go ahead and stop here and stop recording. If you have some questions, stay behind and I'll answer questions. I'm gonna stop sharing and stop.